So I'm going to talk about linalg.pack and unpack operations. To give you an example why those ops are useful, here's a very well-known blocked mathematical algorithm. So in the first iteration, we used the red values to compute the partial result of the blue values, and in the second iteration, we used the green values to then get the full result. If we look at the in-memory layout, it actually doesn't look too bad. So some values are close to each other, and we can get some locality out of that, and the cache misses are not bad. And this is a very well-known, well-studied algorithm. But when we look at it, there's still a few holes in it, right? So the red values are not all next to each other. In a packed layout, we actively change the values in memory, so we get consecutive loads all the time. So this is the same matmul, now a bit reshuffled. And the red values are all next to each other in memory. We can load them, it's very nice, and the green values are all close to each other again. On the right side, there's the next iteration. You see again, very consecutive loads, and we get very good cache locality with an algorithm like that. So this layout, if we change something to that, it's called packed layout, or the algorithm to get a matmul to that is often called data tiling, like my colleague Ege told you before. However, to understand pack and unpack, you have to reshuffle a two-dimensional tensor to a four-dimensional one. And in my mental model, I always first apply like a view on the tensor. So I start from logical two-dimensional tensor and then apply the 4 dimensions onto the tensor. And you see the red, green, blue, and orange, kind of orange lists that are created so far. So we didn't change any layout so far. This is just indexing that we changed. The packed layout then takes that indexing and actually linearizes it in memory. So this is reduction tree just to show you now we have 4 dimensions instead of 2. And these data movements are of course not free, and I will talk later about amortizing them. Let's go through a few examples of the pack and unpack ops. So here you have a pack op, and one thing it can do is actually pad the tile sizes to a specific size, to example, to use tensor cores on your GPU. It does that by getting an argument called pad to get the right values, and then the inner tiles is actually bigger than the input size. So the input tensor is 3×1, and the inner tiles is 5×2. And what it then does is it actually pads in between the dimensions, and you see that the red, green, and blue values are now not next to each other, but closer apart. If we can create a padded tensor like that, we also have the reverse of that, which is unpacking a padded tensor into something that is not there anymore. So here you see the input tensor is of size 1×1×2×3, and the output is of size 1×2. The inner tile sizes kind of mirror again the input sizes, and the pack op basically checks if the number of elements in the result is smaller than the elements of the input tensor. It will then do an extract slice that is not having the full dimension of it, but only a subset of it. Those ops also support dynamic shapes end-to-end. So here's an unpack op. The input is dynamic, but 4-dimensional. The output is dynamic. And now the inner tiles have arguments for tile n and tile m. It looks like it's part of the attribute. It's not, it's just pretty printing. It's an argument to the operation. So what happens now when you lower that is that you get a bunch of tensor.dim dimensions in your code. First, to create the tensor.empty that you know from linalg, you then transpose the values, collapse the shapes, and then because you need to be able to make the reverse of padding, you actually have to get the dimensions of the output tensor and then do an extract slice of the size of the output. And at the end, you have a linalg.copy to the result. The linalg.pack operation also fully supports dynamic shapes. Some interesting observation I had when I put together the slide deck is that this operation as is doesn't lower. but the unpack does, and when you look at the code, it's like an error or like notify match failure from 2 years ago saying that the insert or extracts, the insert slice is not powerful enough, doesn't support dynamic shapes. It does now, so I think just no one needed to have this lowering as is. And one of the main pain points of the linalg.pack operations come into play when you have unit dimensions. So unit dimensions are dimensions of size 1. And you get them very, very often in UIR because you generate a packed MMT, like a packed layout, and then you apply tiling to the outer dimensions. And at the end of tiling, the outer dimensions are very often 1 for you. There are a few patterns that do special handling for unit dimensions because they appear so often in the code. And the tricky thing is always that a dimension of 1 is kind of a weird case. It doesn't do anything, but you have to account for it. And there are a lot of errors happening there, but I think now most of them are done. If you look at this operation itself, it actually doesn't do anything other than changing the view of the tensor. So the 4 elements are still there, and every dimension was of size 1. However, there was a test case or an operation that we needed to fix upstream, and we added test cases for that. You can also have now untiled non-unit dimensions between unit dimensions and get special handling by that. Andre did implement that a few weeks ago. Very handy. So what do we get from that? If we can make use of a data-tiled layout and amortize the cost of the memory movement, we get very, very good speedups. I forgot to mention that this is tested on the Orion 06 board that AGA also used for its benchmarks using the Neon instruction set. So the naive blocked matmul is already quite fast, but when we can amortize the cost of the data movement, we can get new speeds that we didn't see before for algorithms like that. So it ranges from 66% to a decrease of 92% in latency. So how do you use it effectively? If you only have a gem kernel, very often, or most of the time I would say, you will not see a performance increase when you move to a packed layout. To see a performance increase, you need to move to something like an AI compiler where you can fuse the packing into the producer op, so you kind of hide the latency associated with reshuffling in memory. If you can do something like that, like we use Erie under the hood and there's support for that, you can get very, very good performance out of that. And what are some unexplored paths so far? So if we go back to the benchmarks, most of them are very matmul heavy workloads. We also care a lot about convolutions, and data tiling for convolutions is something that we didn't explore so far. We didn't have time for that. Another thing is about the design of the linalg.pack and unpack ops. It's attribute-based. If you look at other projects like Triton, they have a matrix to represent this reshuffling of memory. And in my opinion, that one is a lot more elegant than our attribute-based approach. And if we explore something like that, we could maybe apply that automatically to something like a linalg generic and then create the linalg.pack and unpack ops with that. You can then have, I don't know, a matrix that represents your data, like your memory hierarchy, and automatically apply that non-generic ops, which would be very nice. And with that, we are off to lunch, and thank you for listening.